Okay, 5:30.
5:30.
Okay. Yeah. I think we reached into this energy quantize the last time. So we can have a discussion about this energy. First, we know this is quantized because now the allowed energy is not continuous, right? And take the quantum number, we call this a principal quantum number. Most number is from 1, 2, and all the infinite number. Then now let's discuss. First, let's consider the ground state. Ground state energy. So that means N is lowest, right? N equals 1. Then from this formula, E1 is minus mu e to the first power 2.5. This is a constant. And here, let's consider, remember, because the mu is a reduced mass, remember, that is m e m per term, and denominator m e plus m per term, or m e divided m per term up and down, so we have m e or m per term times 1. So we know the per term, or just this ratio, okay, is much smaller than 1. Since per term is much larger. So we can approximately, that is replaced by the mass of the electron. Then here, this E1, so ground state energy is, we can take this M E to the fourth power 2h plus 4, which is minus 13, famous number, right? So this famous number is, because it's constant, so we always take as one reference. Then we can also write any energy at any level higher than the E1 is minus E1 over N squared. So that is simple to remember this number. So that is discussion about the ground state energy. Okay. Then the second one, let's discuss the degeneracy. Degeneracy. So given one energy level, how many states, right? That is we are going to discuss. So now let's see here. Degeneracy is, let's use L, and then we can have that's N, E, L, right? And then, for given N, we can allow the NR. I'm going to, and L. And for given L, we have L, right? So that is how many the degenerate states for this case we have. Okay, let's discuss. So N is from smallest one equal to 1. The N equal to 1, that is energy ground state in the E1. Okay, fine. How about NR and L? If you remember here, this relation, right? So with N equal to 1, L and NR should be always 0, right? Because we have 1 here. So there should be only one choice. And then when L equal to 0, M equal to 0, so that is not degenerate, right? Only one state. Okay. Now let's consider how about N equal 2. N equal 2 we have followed here, right? Oh, sorry, that's not my, because I already observed my sign here. So then that is E1 over factor 4, because 2 squares is 4, right? Then now we are going to discuss how about the possible value for NR and L. If NR take 0, L must take 1, right? Because 1 plus 1 equal to 2. So then L equal to 1, so we know M is 0, sorry, yeah, 0 plus minus 1. We have 3 values for giving L equal to, so that is one case. And then if Ni equal to 1 is also possible, so L must be 0. So for this case, how many states? 4. 4, right? So that is psi 0, 1, 1, 1, 0, 0, psi 1, 1, 0, and psi 1, 1 plus minus 1. For states, right? Now let's keep continuing. You will see you can find this or formalize this degeneracy. So that then here this is a 3, this is 9, right? Then for this case, if n equal to 3, we have if Ni to 0, L must be equal to 2. If Ni to 1, L equal to 1. Ni to 2, L must be equal to 0, right? So we have 0, 1, 2. So then this is a 2, 1, 0. Yeah. Okay, so here if we say the orbital is a p orbital, right? S orbital, d orbital, p orbital, S orbital. Now when L equals to 2, M we have 0 plus minus 1 plus minus 2. L equals to 1 we have 0 plus minus 1. And L to 0. So how many states? 5 plus 3. So 9, right? Okay, the state is also you have 2, 0, 2, 1 plus minus 1, 2, 1, 0, sorry, 0, 2, 2, 2, 0, 2, 2 plus minus 1, 2, 2 plus minus 2, right? So 1, 2, so 3, 4, 5, and then we have another 2. Okay, then keep going. So you will see here, for n equal to n, right? So energy is E1 over n². Then the nr start from 1, 0, 1, 2, until n minus 1, right? You see here. When n equal to 1, n minus 1, 0. When n equal to 2, n minus 1, right? So that means they all allowed nr is from 0 to n minus 1. And similarly for L. So for L, this is m minus 1 and m minus 2 until this 1 and 0, right? Okay, and so this one is just m over 0 plus minus 1 plus minus 2 until plus minus 0 and all this, right? Now here, how much here? We are going to determine or find the formula. Okay. So if you can see here, for given n, I'm going to determine Gn, right? For given n, how many states that correspond to the same energy? Then that means how many choice for L, since you will see here, for given n r, L is also given. So that means we just select this one also fixed, right? So that means for given L from 0 to, we can select L from 0 to n minus 1. All the L give the same energy, right? To n minus 1. And for given L, we have m from minus L to L, right? So those states. Or you can write down here L from 0 to m minus 1, because this for given L is 2L plus 1. Oh, sorry, this is not 2. So that is this sum. This sum is simply the arithmetic sum. Right? That is,
Dr. Yu?
yes.
I'm having a little bit trouble wrapping my head around how the same wave function,
Yes.
psi 100, can be in both 1 and 2.
Okay. All right. So here, because for n equal to L has 2 volumes. So because you see n equal to 1, they form the same energy. So for all the first number 1, the remaining all the L is follow that energy. that is the geometry. Yeah. That makes sense now?
Would that be n equals 2?
This
2,
is n
0,
equal to
0?
1, this is equal to 1, this is n equal to 1, right?
Because that's in R. Wouldn't that
This-
be n equals 2 though?
Now here, this is the index, right? N, L, M, right?
Yeah.
So now n equal to 1, n equal to 1.
1.
And L have to only 1, 0.
Right.
So when n equal to
2.
2, oh, sorry. That is my mistake. Oh, wait a moment, yeah, I made a mistake. Yes, you are right.
Okay.
You're right, yes.
That makes sense.
And then there's a 3, yes. Yes. That is my mistake, yes. That makes sense, right?
Yes,
Okay,
of course.
thank you for correct that one. So for this one, we know for this arithmetic sum, we know that generally the sum is, if the sum is, this one. Okay. If we just direct use this one, so that is, I use index of n minus 1 since we have L from 0 to n minus 1. And then this is n L, right? So that is n A L is 2L plus 1. So for this summation, we know that to give us half of A, the first term, which is A naught plus A to the last one is n minus 1. This, if you remember this. So that is simply half of A naught when L equal to 0, so that is 1, right? And when L equal to n minus 1, so that is 2 multiplied n minus 1 plus 1. Then you can see here 1 minus 2, 1, so that cancels. So we have factor, so we have, here, sorry. It's my mistake here. So that is cancelled. That gave us, because, so here, this is. And you can double check here. This is equal to 1 squared. This is equal to 2 squared, 3 squared. So here it is n squared. This is we derive this the formula to find calculate how much the geometry, and by analyze this relation between for given n, how much allowed L and then how much allowed M. Then we can have this all the states correspond to the same energy level. That is the geometry, right? Okay, there's a second discussion now, number 3. So now let's look, if we have this hydrogen atom energy, we can extend to hydrogen-like atom. Hydrogen-like. Actually, not atom, I, right? Indocent atom, but we know that is I. So in this case, what is hydrogen-like means? If we have an atom, inside positive charge is not electron, one electron, but Z, atomic number Z, right? And this electron move around with R. So the difference between this one and the hydrogen is that the hydrogen, we have Z equal to 1. So if Z equal to larger than 1, then we know that is atom and all the remaining electron here, ionized, only remaining 1. And so center is this one. Then the potential, in this case, potential R is a function of negative. So you see, if you remember, for compare with hydrogen atom, the potential difference only we have factor Z here. So all the other things, then you can do all this procedure we can obtain. Then finally, the energy allowed energy is same thing. The only difference we have factor E, okay, En for the hydrogen-like is equal to minus now mu here. This is E to the fourth power means because the potential is E squared. So that is E squared to the square. Then here, replace E squared by the Z E squared, so we have Z E squared. squared. And the others are same, right? So denominator is 2h bar squared and n squared. Now, if we define the E1 is this number, so you will see it is E1 over n squared and d squared. The only difference that multiply this factor here. So all these other we can discuss same thing. That is the hydrogen-like atom. We can have the energy spectrum very easily, and also the wave function follow the same thing. Only the factor here, just keep in mind, replace E squared by E squared. Okay, this is we discuss for the energy. Now we continue discuss all the other solution of wave function. So by this solution, that is for radial wave function or radial function, which when low go to 0, controlled by low to the L's power, when low go to infinity, controlled by this exponential, and the intermediate is by this F low, which is truncated confident hypergeometric polynomial, right, or function. So now let's combine those together to write the final radial function. So number 4. Let's radial function. Function finalize here. So okay. R, since we have index n, L, right? That we have this the truncation here. This truncation S max depends on n, right? Because nr and n. So nr equal to L plus 1 minus n. So that means for given n and L will have one function. Therefore, the radial function now we introduce these two index. Previously we didn't say, right? I didn't give any index, just functional like this. But now, for given n and L, it has different. So now, it is here first L's power, right? Minus half low, and this is F. A here is L plus 1 minus n, and the B is 2 L plus 1 and rho. Here, A is this one, right? And beta is n. So here you see here, if this is n, so A is L plus 1 minus n. That is replaced here. This is A, right? So that is function. Then if we because we load, remember we introduce rho is 2 alpha r, right? And alpha we know that is 2 alpha is 2 mu. Absolute value not en. We have index in here. H bar squared r. And finally you just substitute the energy. Then finally we can find that is 2r over a naught n. Here we introduce a naught, which is for moment radial. Okay, then we just replace low by this one, so now that's a function of r. So finally, r, now I'm going to replace low by r, r, capital R and L as a function r, which is now, I'm going to give you the normalized constant here, and I'm going to explain what is L. Capital N and L, which is the index of L, a naught n to the L's power, since here, this is a log, right? So now log to the L's power is this one, and exponential here, half log. So we have a half, this factor 2 is cancelled, right? So minus r over a naught n, right? and F. So F here, L plus 1 minus N, 2L plus 1. And now this rho is replaced by 2R or A. This is a radial function, and here is normalization factor. Such that we have this R and L, R. So whenever, now we have this, so it is normalized. And here, N, the normalized factor is equal to, I just gave you, because to normalize this function is the details, right? We will not spend time on that. Just give you the result. 3 over 2 L naught, N square, 2L plus 1 factorial, square, N plus L factorial, N minus L minus 1. So now we have the real or explicit expression of the radial function. Then we can discuss the behavior of this radial function. Then we go to the final radial function of this type of function. First, if the radial function here, so now we are going to find this, since I use this truncated complement hypergeometric function, right? And the textbook is this Lagrangian polynomial. So we need to find the relation between this one and the Lagrangian polynomial, so you can convert to the textbook. So because for this, if given the index PQ, this is a Z, for this is a called associate. This has a relation between this one and this truncated complement hypergeometric function is a summation of minus 1 to the q's power and the p factorial square, then q factorial, p minus q factorial, and then correspond to this truncated complement hypergeometric function. A is minus p minus q, and b is q plus 1. Then the variable is z. So we have this relation. Or now, or then the complement hypergeometric function is equal to just reverse, right? So that is minus 1 to the q's power. And then this q factorial, right? The denominator becomes numerator. Factorial and p factorial is square and the here associated polynomial. So if I have this, okay, now we are going to replace this one here. Replace this and write the radial function in terms of the associated Lagrangian polynomial. But then we need to find what is q and p correspond to. Here we have L and N, right? So that is A and B. So this is A, this is a B, right? So now we are going to find, because q plus 1 is B, so be equal to 2L plus 1, right? That is B. Then from here, q equal to 2L plus 1, right? 2L plus 2, so cancel. So that is, and the second one, minus P minus Q is equal to A, right? A is L plus 1 minus N. Right, that is A here. Then we can have, and we substitute Q equal to 2L plus 1 here. Finally, it's very simple, so I just give you the final result. So L plus N. Then now we have a final radial function. Okay. Final radial function for given N and L as constant R, which is here I have the N and L and 2R, that is the low initially, with the L's power, exponential. And now this F, the truncated complex hypergeometric function, I'm going to replace by this, right? So here that is minus 1 to the Q. Q is 2L plus 1 power, right? And the Q.
Would this be minus 1 to the minus Q power?
Minus 1 to the, yeah. You mean this one?
Yeah, because if you're dividing by minus 1 to the cube, or
This one?
am I wrong there?
You mean this one?
The minus 1
Minus 1.
to the power of q.
Yeah, this one?
Yeah, if we divided that factor to the other side,
Yes.
and it was positive, would it become to the power of minus q?
Minus Q, Q. Yeah, for the 1 is the same, right?
Right.
That makes sense?
Yeah.
Yeah, for 1, but it was minus or the plus is the same because it's 1. That makes sense? Okay, so I just keep it, okay. You mean this one to here,
Yeah.
right? Yeah,
Right.
yeah. Okay, so then that is this one, and now the Q is 2L plus 1 factorial, P minus Q. Here we have, okay, just give you, P minus Q is minus this one, right? So that is nothing but that is minus that term. So that is, let me see, P minus Q is, so if it's a minus, so then M became plus, this became minus, right? So that is M minus L minus 1 factorial. That is this one, because this is A, P minus Q is A, and A is L plus 1 minus N. So that is this one, right? Then the denominator P is this one, this one, L plus N. Sorry. Okay. Then associate that there's a 2L plus 1, which is Q, right? And then P is L plus N. Okay. Then the variable is here. If you use that is 2R or A, right? And now, if you remember N here, we have also the factorial here. So you can see here we have M minus L plus 1, minus 1 denominator, but that is in the square root, and we have 1, so we need square root inside, we have another one. So just substitute N L there, and you will see finally I'm going to give you the N L prime, which is a textbook has this number, so I just come down to consistent with the textbook. And exponential minus R over 3 not N. And finally is associated that there. Okay, here N, at the N and L1 is, we also observed that because here, minus 1, 2L plus 1 is odd number, right? So always negative. So that if we observe that negative here. This one observe here. So the negative, and this is a factor over A not N to the 3 over 2 power square root N minus L minus 1 factorial and then 2N N plus L factorial. this is a final, or if we want to connect to our solution with the textbook, so we have this convert from the truncated common hypergeometric function to the associated Lagrange polynomial. Okay, that is the number 5. The number 6, the property of this one will has m minus L minus 1, no. What this means, because here, whatever this one, or because this function is polynomial, where's my list? Remember that is related to this summation, right? If I use this complement hypergeometric function, so that is s from 0 to the x max with nr. nr is L plus 1 minus n, right? Minus n. Minus L minus 1. That is nr. Remember? Okay, so that is no, just get it. Then summation a s b o s and this low. So now this 2r n naught n over s power s. So that means this one is polynomial, and this polynomial is controlled by the last one. So correspond to the last one is r as the highest order for taking n is, which is r n r, which is r to the n, right? Correspond to this power. That is because, I just give you the reason, because here. So we have those notes, and give you some idea, examples, see how it looks like. So examples here, for example, R, the first, the lowest, right? R with A to 1, L to 0. Okay. So the nodes, the number of nodes is m minus L minus 1 is equal to 1 minus 0 minus 1 is 0. No nodes, and yes. So that is R1 naught, and the function R is like this. No nodes. Right? Nodes is 0. Number of nodes. Okay, so equal to the number of nodes. Now let's consider the second one. R, and another example, R20. So that because n minus L minus 1, in this case n equal to 2, L equal to 0, so that is 1, right? So we have a 1 node. And then the curve is like here. R2 naught is like this. Here, node. So you can use these numbers to determine or to estimate or evaluate how many nodes of the real function that is just controlled by these numbers, because it's the power series or polynomial, the highest power for taking n and L is controlled by this. Now another example, R21. So because m minus L minus 1 equal to 2 minus 1 minus 1 equal to 0. So that is 0 node. In this case, 0 node. Even if n equal to 2. And then another one I just gave you 0, because m minus L minus 1, in this case 3 minus 0 minus 1 is 2. So we have a 2 node. And what's it look like? So we have 2 nodes here. Now the next one, the for fuel number 6, right? Number 7. Fuel radio function. See the table. 6.6. The most commonly used n equal to that's immediately right now. So n equal to 1, the lowest. So n equal to 1 goes to 0, right? That is exponential, right? So 2 over a naught 3 over 2 exponential minus. You just enter from here. N equal to 1, right? N equal to 1, those terms 1, so we have a 2 over a naught, and then here this exponential and this one is 1. That is one case, and that's the 2, 0 is square root 2 a naught 3 over 2. Then we have r dependent this term. R21 is 2 square root 6 a naught 3 over 2 r over a naught exponential r over 2 a naught, and others. Just go to the table. Okay, once we have this the radio function, now finally we can have the radio, the total wave function. So now let's see how to get the total wave function. Just be the radio part products or multiply this angle part, right? So 7, the total wave functions. That is the psi r theta, right? N, L, M. So given quantum number N, L, and M, just be R, the radial part, and multiply this angle part. Just remember this one. So the detailed radio I already write down there, right? So for this just remind you, right? Because the angle part is chapter 5, so now I just remind you. I write down here m's power, a plus 1, 4 pi, a minus m factorial, 3 plus m factorial, and this associate degenerate polynomial. It's a sigma exponential pi e I n phi. Okay. Now, what we do just substitute those together. Then we can have now we have this total function to normalize. Since both are normalized, right? Normalized behavior. So now we are going to do is. If I do not write down anything, so that means integral the whole space, right? So that is N phi per dr. Then that includes the radial part from 0 to the infinite, N R and L, and the angle part, solid angle. This is a harmonic function. This one, I think I will use this one is equal to 1, right? This one equal to 1, and this one also normalized equal to 1. Yes, already normalized. So that's good. So when we will deal with this, even though we deal with the integral radial part, angle part, but each part already normalized. So when you make this type of integral, if part of them, you know that it's already normalized. So you don't need to worry about the in particular discuss the probability, right? So that is the field function of this. So let's consider the first one, the ground state 1, 0, 0. From here, that's equal to R 1, 0, R, and Y 0, 0. Finally, is pi A naught 3/2 exponential of the ground state. Only function radius, right? So we know that is a spherical S orbital. It's a symmetric, spherical symmetric, right? And the second one, first set it 2, 0, 0. Of course, first excited we have the degenerate. The degeneration is 4, right? So we have 4 wave functions. 2, 0, y 0, 0. That is 1, 4. This one textbook it do not have, so I just write down here in case if you need this integral, you can use this function here. Second one, L equal to 1, 2, 1, 0. But m equal to 0, so that is R2, 1, Y 1, 0. Which is 2 pi, 1 over A naught, 3 over 2, R over A naught, exponential minus A naught and cosine theta. Now we have an angle dependence. So we know this like the orientated along the x-axis, right? That is the behavior. Wave function. 2, 1 plus minus 1. Another 2, which is R2, 1. But y is 1 plus minus 1. I'll give you 1 over 8 square pi. 1 over A naught, 3 over 2. And here R over A naught, exponential. R over 2A naught. Now here it is a sine theta, and also multiply this plus minus 5. That along z-axis, rotation. So you can see here this behavior is like this, right? The ground state is a spherical, and first this one is still spherical, but we have it's not a sphere, but inside it's hollow, right? So that you can see that it's 2 circles, and then this this one is along z, so we have a cosine, and this along the x and y axis. All right, so that is the total wave function. Now we discuss probability. How to find the probability, determine the probability to find the electron in the certain volume or certain location, right? Now we discuss number 7, 8 for probability. So if we say that, how about this one? P. I use P, and for given number n Lm, which is the function r theta phi dr, that is the square of this total wave function. And drq, right? So drq is r dr, r squared dr, and d omega is equal to the volume, right? So this means that the probability of finding the electron the volume element, So, of course, this is for between R and R plus dr and omega. But this is for inner space. The one small volume element, what is probability? So that is the square of this total function multiplied the volume. That is the case. And then the second one, if asked, now I'm going to this only function R, and let me first give you this result, and then I'm going to see what is, give you explain what is. If I do this, d omega square dr is equal to this one is 1, right? Because normalized to the whole volume. So that is the radial function. So what's the probability of this?
1.
No. What does mean this probability? Not 1, because this is a still volume. So this is, I integral the whole direction, right? So that means I just looking for if the electron in this sphere shell with at R and R plus dr, that shell, how much probability? So whatever this the orientation, so that's something like this. This is the probability of finding electron in shell, spherical shell. Right? So that is because the angle dependent spherical shell located between R and R dr. So if I plot here, if this is R, this is dr, so the probability to find this electron in this shell. Then the question asks you, what is the probability to find the electron in this shell? That means the locations is dependent R, so we have all the orientation, all the integral is this one. Integral, all the angles, right? That is the one of the probabilities. So then you can see here, since it's only given in the quantum number n and l, therefore this probability only the index of n and l and function of R, not function of theta and phi. This one is for given orientation, so solid volume certain orientation, right? So we have a given R, given theta, given phi. That is probability to find the volume maybe they are located. If I want to write down log rho. This one is log k at R and R plus dr and omega between omega and omega plus d. The trick, right? That's solid volume element. So, what kind of question ask you to think about how to obtain that probability? Then if we ask you, okay, this I'm going to integrate from 0 to a P n L R dr is okay, what is probability of this? if without integral, we know that it's probability to find a very thinner shell, spherical shell. But now if I integrate from 0 to a, that is all, that is from here to here, if this is a. That is sphere, right? Solid sphere. So that is the probability of finding the electron in a sphere with the radius of a, right? That makes sense? So that's different if I integrate from. And now, to extend, if I integrate the whole, this, how much? That's equal to 1. So that means the probability to find the electron elsewhere, somewhere, let's say, whatever. So that is the, okay. Something. So we have whatever it exists, then that be have that probability, so that is only 1. Because if B exists, cannot be disappeared. So now, last one I want to say, if I do the integral is from 0 to the infinite only for the radial part. Not angle part. And, so that is radial part, only the radial function. And the angle part is only the harmonic function square of this. And then we know this is equal to 1, right? So that is only if you remember, okay, the spherical harmonic has this associated Lagrange polynomial and this exponential EIM plus IM5, but that absolute value is 1, so that is proportional or controlled by only by this associated polynomial. Okay, here only is 5. So only depends. See, that does not depend on 5. Right? Okay. So what is this probability? We are going to look at this given certain the solid angle, and with that, so that given certain theta, right? So certain angle. Then the probability that we do not worry about where it is close to center or far from center, but just along that segment is solid angles of probability of finding. Since we all integral all the radius, right? So that from it's just like corn, right? That is finding electron in a segment between Okay, this one is the example of this. Okay, this is for giving. Actually, because this does not depend on phi, so that is if the integral is this one. Right, so that's for all the radius and extended. And some of them has a symmetry, some has this kind of shell. So that is the picture gives you how we can find this probability of finding the electron. Okay, so this is a several discussion, and from the probability of this solid, the volume element, then depending on the question, you can either integral with the angle or with the radius and try to find the probability in different locations. All right. So the last one before we go to the next topic is we want to let's check. I think this is a question 8, right? 9. Look the average of, because this is sometimes important when we do this sum of a quantity like transition probability, or in chapter 10, consider if we have energy level, the electron here, and jump to the higher energy level, what is either it's forbidden or not forbidden, or sometimes we need to find this expectation value. We need this one because this R. So the only function this is equal to from 0 to the infinite. And is this one, right? So there are some special integral for this. We need to familiar with this, and there's equation to give us to determine this. So to do this, there's we call the Cramer's recursion relation. For any k, so now the relation is like this one. K plus 1 divided by n squared, then NL R to the kth power, and NL minus 2k plus 1.
Did you say this was determining whether or not one transition is forbidden?
Yeah, this if this 0, you sometimes this is sometimes you use that, but maybe sometimes we also do this expectation value for any the sum of operator. Hamiltonian's energy already gave us, but some others, so we need this one. Then let's try to know how to do this integral. If we know this, we don't need to do the details. So that is use this recursion relation here. R to the k minus 1 and L and plus k a naught square over 4 2L plus 1 square minus k square and multiplied with L R k minus 2 and L equal to 0. Okay, so now let's play. Try to see how can we get this like this integral with different k, the power. That's for example, k equal to 0 case. Suppose k equals 0, so now we are going to here, right? K equals 0, so now this is 0, right? So 0 plus, so that is 1 over n squared, right? K equals 0, and there's n L R to the naught, R naught, right? So that is 1. Then second one minus 2k, so that is k is 0, so that's 1, so that's a naught and L. K equal to 0, so this is R minus 1. Right? And the last one, this third term, k equal to 0 is 0. 0. Then this one is normalized, right? Okay. And L R naught and L is and L and L, right? That is normalized. So from here we can obtain this one, 1 over R integral. So the N L R minus 1 and L. I move this to the right hand side, that's equal to this one, and divided by A naught, right? So that is very simple. One over N squared A naught. Yes, over N squared A naught. Okay, so then that first term we can have, at least this one you use this recursion very easily. Now let's go to the next k equal to 1 case. So in k equal to 1 case, here the first one is 2 over N squared here, right? And NL R2, R1, sorry. R1 is R, right? And here. First one. And the minus k equal to 1, so that is 2 is 3, right? 3 A naught and L k equal to 1, so R1 minus 1 is R naught, which is normalized. And the third one is this term k equal to 1, so A naught square over 4 2L plus 1 square minus 1. And L k equal to 1, so this is R minus 1, right? Equal to 0. Now here, this one, that equal to 1. Then we know this one from here. So we already know this term from here, so we can find this one, right? So N, L, R, and L, we just move the term, and I give you final result. It's very easier, so that is half of 3N squared minus L plus 1. So I have this one and this one. Now we can continue. One moment. K equal to 2. K equal to 2. Let's see. So this is a 3, right? 3 over N squared. And L R to the square and L. Okay. Minus 2, so that's 5, right? 5 A naught and L R 2 minus 1, right? And L, the second term. Last one, last, so K equal to 2, the factor, of course, that is A square over 2, right? And then 2L plus 1 square minus 4. And L R 2 minus 2 equal to 0. Right? So this one again, that is 1. This one is this term. So from here we can find this R squared integral. So R squared and L, R squared and L is equal to, we just use this one, so that is this term, and that term we can use. That gives us is half of N squared, 5N squared plus 1 minus 3L plus 1. In the homework or the exam, if you deal with this, you just use the result. I don't even ask you to do it, right? So, okay. One more we have a little bit time. Now, this case is special, so I'm going to give you. That is a textbook already derived, so it gave you this result. This is not from multiplication. That's one, but we are going to use this one to derive others. 2 over n cubed plus 1 n naught squared. This is the problem 6.2 in textbook on page 330. So this one derived from the differential equation of radial differential equation, and then got this one. Then we can use this. This is another case, right? So we have already several cases. Then the last one, we can also derive this k equal to another one, k to k equal to minus 1 case. K equal to minus 1 case. So here, so this is 0, right? Because minus, so that term disappears. And that minus becomes minus 1, so that is plus 1. A naught here. Minus 2 plus 1 is minus 1 plus. A naught N L. K is minus 2, right? R minus 2 and L. And then go to here. Minus A naught square over 4. And 2 plus 1 square. Minus 1 because 1 square is 1, right? And then this NL R minus 3 and L equal to 0. So we can determine this interval. Now here is more. So here we already have this from here, right? Substitute this 1 over R squared, the integral here, and we can get 1 over R cubed. So NL 1 over R cubed and L is equal to, so that is L, sorry, 1 over, sorry, 2 over n cubed L plus 1. 2L plus 1 n naught to the 4th power. Those, for example, ask her to find this expectation value of V potential, right? Graph B, then LM. If you use whatever you have a minor here, then LM. Then you take minus E squared outside, because this is only radial part, so the angle part disappeared. Then you just use the result, right? So that is the case. In some cases, ask you to do some expectation value. If you deal with this, you can apply this. All right, we still have time, so now we go to the last topic in the chapter 6. Is think about we have deal with the potential. It is spherical, right? In the central force problem, we have the potential all has a spherical symmetry. So with such highest symmetry, we know that the geometry is high, right? That's spherical symmetry. For example, we have isotropic harmonic oscillator, right? Or the hydrogen, right? These two systems we already deal with. You know, this high symmetric, we have a high degeneracy. This case is G and E, remember? Tn is n plus 1 multiplied n plus 2. The hydrogen is n squared. Only depend on n, right? Only depend on the principal quantum number. That is highest. Does not depend on L and M, right? And the reason because it's high symmetry. So if we add, okay, if we add external field, field, which is the potential, not, I use vector, has lower hydrogen, lower symmetry. So that means not only depend on radial r, but also oriented with some given some direction. So what happened? The total potential, if I use the total potential of the system, so the potential of this last external, this one also the lower symmetry, since the external. So what happened? That reduce our lefted, the geometry is lefted. The geometry is lefted. So we are going to take one example to give you show what happened if we put this hydrogen atom into the external Mach field. And let's see what happened. Energy, the geometry is lefted, or it will depend on other quantum number, so that means the geometry lefted, right? Okay. Next Monday, I'm going to discuss this example in my field. But just read the question here, and you can think about how this the geometry reduce, and what quantum number will depend on this. Okay, if your homework. Your homework.
I'm going to talk to you in just a second.
Okay, all right, no problem. Yes, thank you.
You're welcome.
Okay, thank you. Today just is what his name? Isaranga. Only him, right? 6, 7. Yeah. Okay. Is he in office? You don't know. Didn't see him.
I didn't see.
Okay. You want to talk to me now or
I can
tomorrow?
talk to you.
Huh?
I can talk to you now. That's
Yeah,
fine.
yeah.
Because,
You don't have a class?
I do, but
do,
I'll
okay.
be quick
Okay.
because I was hoping. I don't know if it's
Yes, tomorrow.
I told you because he
Yeah.
And after
I like-
you teach class 2, I'm finished.
Finished working it through in my head, but I haven't written it down.
I have teach class.
I'm gonna ask him if what I'm doing is correct.
Okay.
Probably before that is not.
I can just send you this.
Whatever.
Yeah, because
Okay.
it's
Yeah, after you are
Manage
finish
the-
class, I'm doing
okay.
मैले चाहिँ उसलाई मेसेज गरेको
I'm
थिएँ
going to spend
टाइम
the night
म्यानेज गर्न
trying-
सक्छ सुरु गर नत्र भयो अहिले चाहिँ स्याटरडेलाई फोकस पुरा भनेर
tonight, like try and because I'm struggling with this right
Okay, okay.
now. So.
If you have some question.